Hello again. So we're going to have a look at the differentiation of circular functions in this lesson. And as we know with our circular functions, we have three types of functions. We have y equals sine, and I'm going to say kx. Okay. We have y equals cos, kx. And then we have y equals tan, kx. Now, the expression of the angle here I'm just showing via the bracket is always kx, the unknown variable being x, and that's what we'll be differentiating with respect to. Now, we have to understand that with our circular functions, there's, if you like, some symmetry, especially with sine and cos, how they're going to match up with the original function and the derivative. However, we won't get into that in this lesson, but I want you to be able to understand or to remember these rules. So when we're talking about deriving sine x, the derivative is we bring this coefficient k out the front and we say cos kx. Now there's no change to the angle, but this factor of k is what determines, if you like, a dilation really of the derivative, but there's a reorientation in terms of cos. So this is our first rule that we must remember when we're differentiating sine. When we're differentiating cos, dy dx, this is going to be a negative k sine kx, and we must remember that. Okay, so that's another rule that you must remember. Now, let's just go to an example here. Before I get to tan, I just want to have an example here. Let's say that I was, y equals something like sine 2x plus pi. Okay. And I'm wanting to establish what dy dx is going to be. Okay, so what I would do here is I would use a chain rule here. So I would say let u equal 2x plus pi and du dx equals 2. Okay, y equals sine of u and dy du equals cos u, and therefore dy dx equals 2 cos, and then we would substitute 2x plus pi in for the expression. So we can see here with this example that the real major factor is this 2, okay, or the dilation along the x-axis if we were talking in terms of transformations. But that's what corresponds to the derivative or affects the derivative in this form. All right, so I want to separate that and sort of now talk about tan. So I'm going to sort of cordon these two rules off. Now, the rule for tan is given by dy dx equals, the k will come out the front, and then we would have sec squared kx. Now, this term sec, a lot of students wouldn't have seen this term sec just at this point. If you're doing specialists, you may have well worked with it. Sec theta is an expression that we use with circular functions, and what it refers to is 1 on cos theta. Therefore, when we talk about dy dx of tan, what we're really saying is we're saying k cos squared kx. But the way that we should always be expressing it is, as I've shown it before, sec squared kx, like so. And that's a rule that you really need to put in your memory bank because you're going to be using it a lot. All right, so now let's have a look at some worked examples. So here I have one question but 4 parts, and we're going to complete all 4 parts, and we're just going to go through them as is. So 3a, what we're going to say is fx equals 5 cos x. I like to put brackets in, it just makes things a little bit neater. 2 sine minus 2 sine 3x. And my expression for this is going to be negative 5 sine x. That's the rule. So what I'm doing is I'm deriving this in parts. So I've derived this first part, and now I'm going to derive this second part. And this is going to be, I'm going to bring the coefficient out the front, 3. I'm going to have 2 cos, and then the angle doesn't change. Yeah, and then I can express this as negative 5 sine x minus 6 cos 3x. Do a quick check to see if I'm correct. I am, and we move forward. So when we come to 3b, okay, I should say that that's going to be our derivative function here. So just make sure your notation is correct. 3b, we're going to have a look at fx equals cos x plus sin x. The derivative f dash x is going to be written as negative sin x plus cos x. And I might just want to write it a little bit neater, just so that I'm leading with the positive instead of the negative. And I'll just check if that is correct. And it's correct. Okay. So now when we're having a look at 3c, the function is given as fx equals sin x plus tan x. So this is the first example that we are using a derivative of tan. Well, we know how to derive sin x, so that's not going to be problematic. That just becomes cos x. And tan x we just write as sec squared x. Now some people, and I'll do this just in green, some people may want to write this out in, expand it out a little bit further. I would probably not do that. I'd just keep it in terms of sec squared x, but they might want to write it like so. They could do something tricky here where we could do, let me just come up here, cos cubed x on cos squared x plus 1 on cos squared x, and then that equals cos 3x plus 1 all on cos squared x. So you could do that. What I would say is actually don't worry about that. Just keep it with the sec squared, okay? And that does you fine. That serves you fine. You don't need to try to complicate things any more than what they already are. So when we have a look at question 3D, we get fx equaling tan squared x. So for this, I'm just gonna rewrite fx as equaling tan x. I don't need to do this, but it sort of just makes more sense because I'm going to have to apply the chain rule here. So what I'm going to say is I'm going to say let u equal tan x du dx sec squared x, therefore y equals u squared, and dy du equals 2u. Therefore, dy dx, which is also equal to the derivative of fx, is going to be 2 tan x. Remember that tan x, okay, that's come from u, okay, u here, times sec squared x. Check if my answer is correct. It is so. And great. I think we have a good understanding of differentiating circular functions.